Hi, so I'm going to talk about almost orthogonal bases for inner product polynomials. My name is Chris, and this is a joint work with Aaron Potechin from the University of Chicago. So this is a typical story about you, an up-and-coming computer scientist, and your function f. You'd like to get to know f better. Well, one way you can get to know f better is by expressing f in the Fourier basis. So for example, if f is a function on the Boolean hypercube, say -1 + 1 raised to the n, and it takes real values, then to express f in the Fourier basis, this just means writing it as a multilinear polynomial in the inputs. So for example, written at the bottom of the slide here, the both1 function takes in 2 inputs and checks whether or not they are both 1. Then this is its expansion as a multilinear polynomial. So for example, if both of these inputs are 1, then this will evaluate to 1. And otherwise, on any other Boolean point, this will evaluate to 0. So why can you use the Fourier basis to get to know your function f better? Well, in the Fourier basis, it's very easy to read off a lot of properties of f just by looking at the coefficients in the basis. For example, you can easily determine the variance of f, or you can determine the influence of each of the individual input bits on the function f. A second property is that the basis is orthonormal, which is nice when the input is random, because the basis functions are orthogonal under a random point from the Boolean hypercube. Another nice property of the Fourier basis is that if you truncate the Fourier expansion to any fixed level, that gives you the optimal low-degree approximation for your function f, which is a nice property to have. Finally, the most compelling reason to use the Fourier basis is that it's an awesome mathematical tool. If you just write your function f in the Fourier basis, oftentimes your problem is just instantly solved, or at least becomes simpler. Furthermore, the Fourier basis technique is also applies to other domains other than just the Boolean hypercube. So here you are again, and here is your function f now applying to a different domain. And here are 3 different domains that you might have. In the first one, you have a function which is the input comes from the integers mod n. In the second setting, the input comes from a standard Gaussian random variable. And in the third setting, the input is uniformly chosen from the interval between -1 and 1. In all of these settings, you might want to express your function f in terms of an orthonormal basis on the input domain. So in this first setting, the orthonormal basis that you should choose are the Fourier characters of Zn, which I've written them here on the slide. They're these exponentials. In the second setting, when the input is from a normal distribution, the orthonormal basis that you'd like to use is the Hermite polynomials, which are orthogonal when their input comes from the standard normal distribution. And in the third setting, the orthonormal basis that you could use is the Legendre polynomials, Li. And just to drive home how useful this technique can be of decomposing your function with respect to an orthonormal basis, I'll give you even more examples. So here are 2 more examples of f that you might be studying. In the first example, you again have a function on the Boolean hypercube, but now your function is additionally constrained so that it only depends on the Hamming weight of the input vector x. So you'd like to express f with respect to the Hamming weight as some function of the Hamming weight. Well, if x comes uniformly from the hypercube, then the Hamming weight of x is distributed as a binomial random variable. Therefore, the orthogonal polynomial family that you're interested in is the orthogonal polynomials for the binomial distribution. And these are well known and studied as the Kraczuk polynomials. The second example is due to Dickstein, Dinur, Filmus, and Harsha. In this setting, f is a function on a high-dimensional expander, x. And specifically, it assigns a real number to each of the I-dimensional faces of the high-dimensional expander. Then you can give a harmonic decomposition of f. So for example, here it is, f minus 1 will be a constant, and the other functions, the higher functions in the decomposition, will have mean 0. f0 assigns to each vertex of x a real number. And then the higher functions have the property that if you just average them around the neighborhood of any vertex in x, then you get 0 again. And so on for the higher degrees. So this example is a bit different from the previous ones because we don't have an explicit basis that we can represent f in. We only have ways to project f to the different levels of the decomposition. And there's actually another technicality, which is that it's not a perfectly orthogonal decomposition, it's only approximately orthogonal. But hopefully these examples serve to convince you of the utility of this approach. Okay, in this last example, you're a bit sad because you don't know what is the basis that you should be using for your function f. So now your function takes in vectors d1 through dm. The inputs are d1 through dm, and each di is an n-dimensional vector, which comes from a standard Gaussian distribution, independently chosen. So for example, here's a picture of what the di's might be realized as. And furthermore, this function f is constrained to be orthogonally invariant. What that means is that for every orthogonal matrix T, if T is simultaneously applied to the vectors d1 through dm, then the result of f does not change. What is an example of such an orthogonally invariant function? One example is measuring the angles between the vectors. So one could also measure the inner products, so d1, d2. And if you multiply several of these things together, that's still going to be orthogonally invariant. And we'll call such functions inner product functions. For, I guess, as we'll see, they can be expressed in terms of inner products of the vectors di's and dj's. So as I said, you're a bit sad because you don't know how to express your function f. Well, fortunately, this is where we come in. So our contribution is to give an explicit, almost orthogonal basis for these inner product functions, at least in the case where they're polynomials, for inner product polynomials. So before I get to the basis, first I want to discuss the space a little more and tell you why we were interested in it. So let f be a function of d1 through dm, these are vectors, such that f is orthogonally invariant. And for the rest of the talk, we will assume that f is a polynomial function of the entries of the different vectors. So as I alluded to on the previous slides, it's not too hard to show that f is a polynomial in the inner product variables of di with dj. So here's an example of a function f that you might be considering. For example, f is the inner product of d1, d2 times d2, d3 times d1, d3 minus 2 times d1, d2 squared, d3, d3. So as you can see, each of the terms in the expansion of f corresponds with a graph on the vertex set 1 through m. And specifically, an edge between I and j corresponds to the inner product between di and dj. And in fact, these correspond with multigraphs, as you can see in the example on the right here. D1, D2 squared means there are 2 edges between 1 and 2, and D3, D3 means there's a self-loop at 3. So in this way, the terms in the expansion of f correspond exactly to multigraphs on 1 through n. And we are interested in these functions in the context of the sum of squares algorithm, in which we were studying functions of a collection of random Gaussian vectors. These functions might also be useful for rounding algorithms for semi-definite programs, because in that setting, you're often only interested in the angles between vectors and not in the absolute entries themselves. And we suspect these might also have to do with multi-overlaps from statistical physics. So just to get a little more comfort with working with this space, let me compute the expectation of this function f. So again, the expectation is over the vectors di, where each one is a standard Gaussian, and they're chosen independently. And I'll represent for now as a graph that we're taking the expectation over. So we have these two terms, and each of the inner products can be expanded because it's just a sum of n things. So we sum over ijk, d1i, d2i, d2j, d3j, d1k, d3k. And similarly for the second term. So if you look at this expression, actually something nice happens. Most of these terms have expectation 0. In fact, the only terms that won't have expectation 0 are the ones where the i's and j's match up so that every variable occurs an even number of times. And the only way that can happen in the first example is if I, j, k are all equal. And if that happens, then you get d1 I squared, d2 I squared, d3 I squared. Those are all equal to 1 because the Gaussian has variance 1. So in fact, this first term is just equal to n because there are n non-zero terms, each of size 1. In the second expression, something similar happens. You must have I equals j, but then k is free to vary. So actually you get n squared here in this second term. So actually, just by thinking a little bit harder about this example, we'll notice two interesting properties of these inner product polynomials. Let's say that I use mg to represent for a graph G, let it just be the product over the edges of those inner products. So as we had here, there were two of them. Then the expectation of one of these terms is equal to 0 if there exists a vertex of odd degree in G. So the only way that a term can be non-zero is if there's a way to pair up all the i's, j's, and k's, meaning all the vertices must have even degree. And furthermore, we can determine the magnitude of one of these terms. The magnitude of one of these terms is given by the max number of cycles in a cycle decomposition of the graph G. That is, given that we can partition the edges of G into cycles, what's the maximum possible number of cycles we can make? So actually, this quantity is NP hard to compute in general from G. So this actually tells us a couple interesting things about these polynomials. First, it's not likely that they have simple expressions for things such as the expectation or stuff like that, because these quantities are pretty hard to determine. So our goal is not to come up with simple closed form expressions, is to come up with somewhat combinatorial expressions of exponential size that will allow us to manipulate these kind of large objects, such as sum over cycle partitions. And I guess a second point to make is that the combinatorics of these polynomials are intricately related to the topology of the underlying graphs G, which is a really interesting feature of the polynomial basis. So to expand a little bit more on what was on the previous slide, let's make the definition. So given a multigraph G on M, we define MG to be the product over the edges of the inner product between du and dv. So just the monomial represented by the graph G. Then here's the lemma we prove, which is a concrete formula for the expectation of MG. It's the sum over perfect matching collections of n to the number of cycles in each perfect matching collection. So what do these things mean? A perfect matching collection in a multigraph G is a perfect matching at each vertex of the edges incident to that vertex. So for example, here I've depicted some graph G. The vertex labels aren't important. Here's a graph G. One perfect matching collection would pair up the incident edges at each vertex. So let me do that pairing now. This is one way you could do the pairing. And once you've made the pairing, the number of cycles in the perfect matching collection is just equal to the total number of closed loops that you made after doing all the pairing. So here we have, that's one loop, and we have a second loop like this. So the number of cycles in this particular matching is 2. So the formula says that we need to sum over all perfect matching collections of n raised to the number of cycles in the perfect matching collection. To do an example, suppose we are working with the cycle graph, which is just the inner product of a bunch of vectors in a cycle. Then in any perfect matching collection, there's actually only one perfect matching collection. Because each vertex only has degree 2, you have to pair them up like this. Just each pair pairs up. And now there's only one cycle in this total perfect matching collection. So expected value of mg is always n for the cycle. Let me do one more example here. So let's say that mg is this slightly larger graph, which is these inner products. then to compute the expectation of MG, we need to sum over all perfect matching collections in G. So what are the possible ways that we can form these perfect matching collections? Well, at vertex 1, you know exactly how you must pair up incident edges. And same with vertex 3, they must pair like this. For vertex 2, there are 3 possible ways to do it. So let me draw those 3 possible ways. Again, 1 and 3 are the same. And 2, you could either pair them like this, or like this. In this first case, there are 2 loops formed by the perfect matching collection, so you get a factor of n squared. In the second case, there's only 1 loop. In the second case, there's also only 1 loop. So in total, the total is the sum of these things. It's just n squared plus 2n. So again, this gives an exponential formula for the expectation of mg over some sort of combinatorial objects in the graph. So now that we've studied that a bit more, it's time to move on to the actual basis for the functions in this space. So let's say that f is some polynomial in the inner products, and it has total degree at most capital D. The basis, we'll write it as PG, where G is a multigraph on 1 through m with at most D edges. The basis function PG will have a unique leading monomial mg. And the degree of PG, therefore, is just equal to the degree of mg, and that's equal to the number of edges in the graph G. The PG will satisfy the following orthogonality property. If the degrees are not equal, then they're orthogonal. In fact, they actually have a slightly stronger orthogonality property, which is that if the graph degree of a particular vertex is not equal, then the polynomials are also orthogonal. So this is what we mean when we say that the polynomials are almost orthogonal, and they furthermore have one other orthogonality property, which is if you compute the expectation of PG and PH, then it's actually guaranteed to be small as long as G and H are not different. It's significantly less than the square root of the variance. So this is the property that the basis will have. So what is the formula for the basis? Well, here it is. So we define PG to be a sum over matching collections in the graph G of the monomial for the routed graph of the matching collection M times a sign, which is just -1 raised to the number of things matched, times what we've seen before, n to the number of cycles in the matching collection. Okay, so the difference with the previous formula is that these are no longer perfect matching collections. They're just matching collections. So at each vertex, we match up incident edges, but you no longer have to pair everything. You can choose a subset of the incident edges to match. For example, here I've drawn this graph G. One way you could do it is you could match up this incident edge here like this, and you could leave these other 2 unmatched at that vertex. Match up this one here, you can match up these here. This is one possible way you could form a matching collection in this graph. Okay, the routed graph is the result of following the matching collections and forming a new graph where you've replaced all the edges by their completely routed versions. So this edge, which previously started at this vertex, if you follow it through the matching collections, it now becomes an edge that goes all the way to that other vertex. And this edge here now becomes a self loop, because that's what happens when you route it using the matching collection M. So this is the routed graph M. So let me give an example of the polynomial for this particular graph G, d1, d2 squared. In this graph, there are 4 possible matching collections. Let me draw them. The first matching collection does nothing. It does not match any of the incident edges at any of the vertices. The second one matches at 1. The third one matches at 2, and the fourth one matches at both 1 and 2. So, okay, let's work out what the term is for this. The M sub route here is going to be d1, d2 squared, and the sine is going to be just 1 because we did not, the size of m is 0. And the number of closed cycles in n is 0. So cycles of n measures the number of closed cycles that we formed. For this second term, the routed graph looks like d2, d2. The sign is -1 because we matched one thing, and there are no closed cycles. So again, this is 1. Third example, we have d1, d1 for the routed graph, -1 for the sign, and again, 1 because there are no closed cycles. In this last graph, the routed graph is the trivial graph with no edges, so that's 1. The sign is -1 squared, and the number of cycles is 1, so we get a factor of n. So overall, the orthogonal polynomial for this graph is d1, d2 squared minus d1, d1 minus d2, d2 plus n. Okay, so that's the definition of the orthogonal polynomials. So we also define orthogonal polynomial bases for inputs coming from other distributions when they're not necessarily Gaussian. And the two cases that we consider are when the DIs are uniform unit vectors chosen from the unit sphere in n dimensions, and when they're uniformly chosen from the hypercube in n dimensions. We're not able to work with general input distributions, but we are able to give somewhat clean formulas for these two settings, in addition to the Gaussian setting. And they have a similar spirit where, again, we're summing over exponentially many matchings in an underlying graph. And again, this is a basis for orthogonal functions, orthogonally symmetric functions on these spaces. So I want to go into each of these two regimes a little bit more. So first, we'll start with the spherical setting, in which the DIs are independently chosen from the unit sphere. And we're looking at functions which just measure like angles between the DIs. The orthogonal polynomials PG that we get come from the so-called Maxwell representation of the spherical harmonics. You may have heard of the spherical harmonics before, and you might know that they are kind of a pain to work with. But if you use the Maxwell representation of spherical harmonics, then this is actually fairly simple because it's just a degree orthogonal basis for functions on the sphere. And they're very similar to the Hermite polynomials. And for that reason, the expressions actually look fairly similar to expressions in the Gaussian setting. So again, we get similar formulas based on matchings in an underlying graph of inner products, but they're slightly harder. And an interesting feature of the spherical setting is that the combinatorics of the graph of these polynomials seems to be related to planarity properties of the graphs G and H, which is really surprising that there's a connection between the unit sphere and planar graphs. So just to illustrate something strange, in the Gaussian setting, it's true that for every pair of graphs G and H, the expectation of PG times PH is always non-negative. Often it's 0, but if it's not 0, it's always positive. In the spherical setting, that's not the case. So for example, if you take K5 and you break it up into 2 5 cycles, as depicted here, one in blue and one in red, if you take the orthogonal polynomials for to the 2 5 cycles and you take their expectation, then that actually is negative. And this is the smallest example with this property. There are other examples with a K5 minor that also have negative. We don't know anything based on K through 3 at the moment, but certainly this is a strange property that these polynomials seem to have. Okay, in the Boolean setting, we consider when the DI are uniform from the Boolean hypercube. And okay, I should clarify what is the function space now. It's the space of functions of these vectors d1 through dm, which are invariant under orthogonal transformations that preserve the hypercube. That is, it's invariant under automorphisms of a hypercube. What are the automorphisms of the hypercube? So there are two types. The first is a bit flip, where you flip the bits by some z. And the second is a permutation of the coordinates, where you apply some permutation pi on the coordinates of the input. So we are considering functions which are invariant under these automorphisms of the cube. Then one should ask, in the spherical and Gaussian settings, we knew what the non-orthogonal basis was formed by. It was formed by inner product expressions. what are the what's a basis for functions of this type anyway? A basis for functions of this type, it comes from generalizing inner products to expressions of this form. So this measures, given an even number of vectors, just sum up the coordinates of the vectors multiplied together. For example, if k equals 1, then this is just taking the inner product between di and dj. For k equals 2, this is doing some sort of like higher order inner product, where you measure the inner product between 4 different vectors. So the result is that we construct a set of polynomials PG, where each g is now a hypergraph on 1 through n. And in fact, it's an even hypergraph, meaning that all of the hyperedges have even size. So either 2, 4, 6, 8, whatever. When they're 2, they correspond to normal inner products. When they're higher than that, they correspond to these generalized inner products. And it seems like the combinatorics of this setting combines some of the aspects of the Gaussian and spherical cases. On the one hand, the vectors all lie on a sphere. They all have some fixed norm. Therefore, you don't have self-loops in the graph, which is a feature of the spherical setting. On the other hand, the Boolean setting doesn't seem to exhibit a connection to planarity like the spherical setting. And in that way, it seems a little bit more Gaussian. So in conclusion, we presented explicit degree orthogonal basis for orthogonally invariant functions of a collection of random vectors. And we studied 3 different regimes or settings in which the random vectors could come from: the Gaussian setting, the unit sphere, and also the Boolean hypercube. And we saw that the combinatorics of these bases is really intricately connected to the topology of the underlying graphs. So we're still looking for applications of these bases. It would be really cool to exploit the interesting combinatorics of these polynomials in order to prove something really interesting about these orthogonally invariant functions. So now that you've watched this video, I hope you're prepared to do just that. Thanks for watching.